So today we're going to start out in section 6.1 talking about the set of rational numbers. As we begin any chapter we're working on, you're going to see the first section's a lot of vocab stuff just to make sure that you and I are both saying the same thing and meaning the same thing by it. So this section's going to start us out much like that. So start with rational numbers. The first one you're familiar with, of course, is fraction. Fraction is actually any number of the form a over b with b not equal to 0. And it is any number. So the top and the bottom can be decimals, they can be square roots, they can be pies, they can be anything, and it be considered a fraction. The value on the top is called the numerator, and the value on the bottom, of course, is called the denominator. Now, sometimes people will use the word fraction and rational numbers kind of almost like they're interchangeable, but they're not quite. Fractions is very loose. I just told you could have all sorts of things in the numerator and the denominator. Rational numbers eliminates some of those options. So for rational numbers, it's actually any number of the form a over b, or something that can be written a over b, but the a and the b have to be integers, okay? So it can't have, radicals on top. I can't have pi in there if it's going to be a rational number. The b still cannot be 0. Now, not to misconceive what's going on, but we're not talking about numbers, or we are going to talk about numbers in chapter 7 that look like decimals, right? Like a 1.4. 1.4 is a rational number as well because it does have a way that it can be written as the fraction a over b, where a and b are actually, integers themselves too. So we're not excluding 1.4 from the discussion. It's just that we're going to deal more with that version of the numbers when we get to chapter 7 instead of here in chapter 6. There are 4 distinctly different, although related, of course, uses for rational numbers, reasons we would like to discuss them and to talk about how to operate with them. The first one is this idea of a solution. So we can solve equations, or they allow us to solve equations like 2x equals 1. So if 2x is equal to 1, then x would have to be 1/2. If we don't have fractions, right, rational number fractions like that, there's not a solution because there's not a whole number or an integer that will work in that number. So it has to be a fraction. So we're able to solve things from that perspective. The next one is partition. So this is an example. It's more of like how we describe our language, where we say something like this: 1/4 of my paycheck goes to gas. So it's somehow breaking a value of something into portions or pieces. So your paycheck can be broken down, 1/4 of it would go to gas, would be the idea here. Ratio is another one. We'll talk a lot about ratios. An example of this one, common to you, would be something like this. The teacher-student ratio is, and I'm going to write it in word form, is 1 to 8. There's another way we can write that with a colon rather, or we can write it in a fraction form. But a ratio is a type of rational number. And the last one that we're going to discuss throughout this particular chapter is probably, or not this chapter necessarily, but throughout this course, it will be in chapter 9, is probability. So probability is something where usually it's involved in gaming, right? What's the probability of something happening? So this is an example. When you roll a die, you have a 1/6 probability, I'll shorten it just to be prob, of rolling a 5. Right, there's this is a standard 6-sided die I'm talking about. So standard 6-sided die, there's 6 different ways that can happen. One of the 6 is the 5. So there's a 1/6 probability. So we're going to start, like I mentioned when we were just chatting about the class in general, with some pictures. So these are pictures that would come in elementary school. They're a little bit more complicated than my daughter has seen so far. She's been in first grade and below thus far. So you're looking at probably second to third grade where you're looking at items like this because they are potentially problematic the way that they're written. So as you're taking a look at these on part A, can you tell me what fraction is actually shaded in of the whole diagram? Can you tell? It's how much? 1/6. It's actually 1/6. So 1/6 is the correct response or the correct value. But if you glanced at it quickly, or if you were a young student looking at it for the first time being exposed to this idea, what might you say instead? You might say 1/4, right? There's 4 different boxes, one of them shaded in. Of course, the problem with that is not all the boxes are the same size. So the only way to make that claim that it is 1/6 is probably visually to actually draw in the same size boxes. So if we take our diagram and we make all of our boxes the same size, it's much easier to see that the diagram is actually 1/6. It's no less true if I don't draw those in there, but it's easier to see it this way. How about the second one, B? It's 1/4. Now again, whoops. What might you be led to think if you're not being careful or aware? 1/5. There's 5 boxes again, right? 5 boxes. If you asked my second grader, I'm sure she'd say 1/5 on this one. She might look at the first one and catch it, but this one she might not, right? Because the boxes are closer in size. So what do we have to do to sort of get the image out of our mind of what's not happening there to do right? Well, one thing to do is that we could erase these right here, right? And then redraw in the pace that's missing, again, thereby making all the boxes the same size. Now, it's not the only way to do it, but it's probably the quickest way to do this particular problem into making the boxes the same size. How about C? How much is that one? 2/7. Yeah, it's 2/7. So I included this one because it's an image that if you glance at too quickly, it's really easy to get it wrong. What might you say if you didn't pay close attention to this particular diagram? You know? You might say 1/3, just sort of visually shading versus not shading. You might also say 2/8. And the reason that you might say 2/8 is because we do see things cut into slices, think pizza, right? 8 very easily. And so it's just visually kind of funny. We don't really see objects cut into 7 pieces very often, right? I mean, we just don't. So this is kind of an awkward looking or feeling picture. Examples A, B, and C are all objects that are a whole object that's broken down into pieces, right? The top 2 are rectangles, the third one's a circle. So we can think about these as being, like we're making a comparison of a part of what's shaded to the whole of what's shaded. Number D is actually a little different because the object itself is a whole bunch of pieces to start with. So if we're still counting and shading, how many are shaded? There are 7. And how many are there total? There's 12. So this is 7 out of 12. But we're making a comparison of shaded circles that are whole circles to circles that are not shaded completely, right? So there's a different image that's going on here than the ones we had before that's equally related to the idea of fractions. So a couple of historical things to keep in mind because they're kind of fun. Fractions and rational numbers specifically, or in general, been around a really long time. So these are some of the places where you see them in history. Egyptians actually used fractions, but all of their fractions had numerators with 1 in them. So instead of writing a fraction like 7/12, the last one we just saw, they would actually write it as a sum of fractions with numerators 1. It's 1/4 plus 1/3. So that's different, right? It's definitely different. We don't do it that way. The Greeks, historically, are credited with adopting fractions with denominators of 60. from the Babylonians, and it's still presently used in the measurement of angles. Okay, so that's another place in history where we see rational numbers making an appearance. Not what I meant to do. There we go. The last one to sort of think about is interesting. It's the Hindu. They developed the modern bar that we use between the numerator and the denominator. And it came into use in Europe in about the 1500s. Okay, that's a long time ago that we've been using this type of a notation. There are 3 different types of models. I think we have time to run through them real quick. They're not long. That we use. We've actually seen 2 of them used already. The first one is called an area model. And it's the picture that we were using with the rectangles and the circle at the beginning. I'm going to make the number 3/4. So you draw a rectangle. There's nothing special about rectangle, by the way. It's just the object that's being spoken of here. It could be circles or something. But you draw the shape that you have, and you're splitting it into, in this case, 4 pieces. Pretty close anyway. And then 3/4 means shading 3 of the 4 pieces in. So this is one model or visual representation of fractions. The second one, the one we haven't seen used at all, is a number line model. So I'm going to use that same 3/4 on all of my diagrams. So in this model, we have our number line, and we're breaking it apart into pieces. So it starts at 0 and it goes to 1. So if I cut it in half and then in half again, I get fourths. So I have 1/4, 2/4, 3/4 would be right here. And then I can put a dot on the diagram. That's a number line model for 3/4. It's a location type of a diagram. And the last one, set model, is much like we saw on the letter D, where it was the shaded in blue pieces versus the not shaded in ones. So if we have 3/4 here, we'd have our 3 circles shaded in and 2 circles not shaded in. I'm sorry, 1 circle not shaded in. Okay, so I have 4 circles, and then I will shade in 3 of them. So that would be a set model as opposed to an area model or a number line model. Any questions on any of those? All right, this is a great place for us to stop. So we will convene again on Monday.